phase diagrams. The phase diagram is sort of a map. And it shows us the state or the phase. And by phase, we mean physical state, solid, liquid, gas. The phase of a substance in relation to its pressure and its temperature. So we graph pressure on the y-axis and temperature on the x-axis. And so we have lines, they're often curves, that represent a set of temperatures and pressures at which that substance is in a state change. So it's in equilibrium between a liquid and a solid, or between a solid and a gas, or between a gas and a liquid, all those possibilities. In between the lines are regions, and those are areas where that particular state is stable. So the lines represent a vaporization curve, a sublimation curve, and a fusion curve. And where those three curves come together, those three lines come together, we call that the triple point, because 3 lines is 3, triple. That is a unique set of conditions in which all 3 states are stable and in equilibrium with each other. That seems kind of crazy, doesn't it? Okay, here's a phase diagram for water. This is not drawn to scale, but just the overall shape. So here we have pressure in torr, and we've got 760 torr marked here because that's interesting. That's normal atmospheric pressure. Here we have temperature. We've got 0 and 100 degrees Celsius. We've got a region for the solid, the liquid, and the gas. Here is our triple point. So if we look at atmospheric pressure, 760 torr, and 0 degrees Celsius, we see that that is on this line between liquid and solid. That's the temperature at which ice melts or water freezes, right? They're just opposites of each other. If we continue at that pressure over to 100 degrees Celsius, we see we're on another line between a liquid and a gas. That's where vaporization or condensation is occurring. So that's, you have both substances, both phases together. If you've got over 760 torr of pressure at 100 degrees, it's going to be a liquid. At 100 degrees, if you are less than atmospheric pressure, it's going to be a gas. This is the triple point, a little bit above 0, and at a lower pressure where solid, liquid, and gas exist together. I'm pretty sure I have a YouTube video. I don't know why I didn't stick it in the lecture, but if you remind me when lecture's over, I'll pull it up. It's pretty cool to see a liquid boiling with solid in it. It just, like, it's kind of trippy. So that's what the triple point is. The critical point is a temperature above which you can't have the liquid. So at this temperature and pressure, that's where supercritical fluid forms, and above that, the line ends because you can't have a liquid. You just have a supercritical fluid. So you should be able to name the different parts of these phase diagrams. If I give you a temperature and pressure, you should be able to tell me what state that substance is in. Okay? So we talk about navigating within a phase diagram. So here we're treating it kind of like a map. So you can start at, now we've got this in atmospheres instead of torr. Again, this is water. You can start here at 1 atmosphere, and you can navigate by increasing the temperature without changing the pressure. And we see that we've got a solid, and as we heat it up, it melts, it goes to a liquid, we keep heating it, it vaporizes and forms a gas. And we can see what temperatures those transitions happen at. We can also just look at pressure changes at a given temperature. So if we are here at 1 atmosphere and 25 degrees Celsius room temperature, and we decrease the pressure of the water, at some point the water will begin to boil at room temperature. And below that pressure, you're just going to have a gas without the liquid. This is one of my vivid memories of high school chemistry. The teacher had a big vacuum flask with water in it, and he hooked it up to a vacuum pump. I wish I had one of that kind of pump. I don't. I need to get one. And he turned it on, and then he began his lesson. And after a while, the water in the flask began to boil. There was no hidden heat source under the bench top. There's no magic tricks at all. The water started to boil. Then he made us all come up and touch the flask of boiling water. Child abuse, right? The first person was a bit nervous, right? You don't touch pots of boiling water, right? Room temperature. Felt just like touching the bench. Just kind of whoosh, mind blown, right? We didn't do that then. But you touch it and you're like, how, what? You're just kind of speechless. Water can boil at room temperature. You just have to suck the pressure down low enough. Any questions about this? The phase diagrams have different shapes for different substances because they behave differently. And it takes a while of looking at these before you can start to kind of see what's going on. It's a little bit like, watching football. And my boys can watch football and they say, oh, this is this play and that's that play. And he missed his block. And I'm like, how do you even see that? But they've studied it, right? It's important to them. So you look at this for a while and you realize there's some differences here. This line has a negative slope. These lines have positive slopes. It slopes the other way. Water is unusual in that its fusion curve has a negative slope. What that means is that if you start at, like here's 1 atmosphere, if we start at a colder temperature, below 0, but we increase the pressure, we can make the water melt. That's what happens when you ice skate. The ice is below 0 degrees Celsius because they don't want it to be mushy, right? Your ice skate with your body on top of it puts pressure on the ice. And that causes the surface layer of the ice to melt. Wet ice is much slipperier than not wet ice. It's not dry ice because that's carbon dioxide. So by putting pressure on it, you can get it to melt. That's unusual. That does not happen with most substances. Most substances, you put pressure on them, they stay solid. Such as iodine and carbon dioxide. Here, if you increase the pressure, it's not going to melt. In fact, if you increase the pressure on the liquid, it will actually freeze. So we see that there's different slopes, different curvatures on these lines, and depending on what the substance is. Now, carbon dioxide, its critical point is at 31 degrees Celsius. That's much lower than the critical point for water, which is way out here. We looked it up. It's like 340 or something. So out here, critical point for carbon dioxide is at 31 degrees Celsius. And that's at 72.9 atmospheres. That's crazy high pressure. Look what's going on at 1 atmosphere. So you've got the solid, you increase the temperature, it sublimes. It goes directly to the gas state. No liquid. In order to get liquid CO2, you have to be above 5.1 atmospheres of pressure. That's why it doesn't melt. It just goes directly to the gas state. Any questions?